In Chapter 4 today, we're going to take a look at 4.3, which is Dalton's atomic theory, and 4.4, which is formulas of compounds. We're going to begin with how Dalton's atomic theory came about. In the 18th century, scientists studied the nature of materials, and several things became clear, some common denominators among materials in nature. They said that most natural materials were mixtures of pure substances. Pure substances were either elements or combinations of elements called compounds, and a given compound always contains the same proportion by mass of the element. This led to what is known as the law of constant composition, which says that a given compound always has the same composition regardless of where it comes from. So the example that your book gives is that water is always going to contain 8 grams of oxygen for every 1 gram of hydrogen, and carbon dioxide is always 2.7 grams of oxygen for every 1 gram of hydrogen. So the question is, what does this mean? This means that water is always H2O in this ratio anywhere on the planet, and carbon dioxide is always CO2. And if you look at the ratio of the masses, for every 8 grams of oxygen, there's going to be 1 gram of hydrogen in water, making it this ratio. Carbon dioxide is always going to be 2.7 grams of oxygen for every 1 gram of carbon, and it makes it this ratio of CO2. So whether you're here or in Siberia, carbon dioxide is CO2, water is always H2O. So these observations were put together by a man named John Dalton, and this is a picture of Mr. Dalton, and he came up with what is known as Dalton's atomic theory in 1808. So there's been a couple of amendments or changes to his theory, but for the most part it holds true. Let's take a look at each one of the steps of his theory. The first one is that elements are made up of tiny particles called atoms, and we know that even today that's true. The periodic table is full of elements, and the smallest part of an element that can still retain the properties of that element is called an atom, and we learned that in the last chapter. Number 2 says that all atoms of a given element are identical. Now this used to be thought to be true. We now know about things called isotopes. And isotopes are atoms that have the same number of protons but different numbers of neutrons. So protons are positive, neutrons are neutral, and neutrons don't add a charge to an atom, but they do add mass. So they're not identical, so all carbon atoms are not identical. Some carbon atoms, and you'll notice that when you look at the periodic table, when it shows the mass for elements, they have a decimal point. So 12.01 is what we look at for the mass of carbon. And this mass is an average number, because ideally you can't have part of a proton or part of a neutron when we're weighing the masses. So on average, the mass of a carbon atom is 12.01 grams per mole of the atom. However, what that means is we have some carbon atoms that have a mass of 12, and some that have a mass of 13, and some that have a mass of 14. The average is 12.01. So not all atoms of all elements are identical because isotopes exist, and they didn't know that before. Mr. Dalton didn't know that. Look at number 3. Number 3 says that atoms of a given element are different from those of any other element. And at this point I just go, well, duh, because obviously a carbon atom and an oxygen atom are different elements, and their atoms are going to be different. So this one's an easy one to know that it's true, and we can remember that one easily. Number 4 says that atoms of one element can combine with atoms of other elements to form compounds, and a given compound always has the same relative numbers and types of atoms, which we just talked about with the law of constant composition. So this also holds true. And number 5 says that atoms are indivisible in chemical processes. Atoms are not created or destroyed in a chemical reaction. A chemical reaction simply changes the way the atoms are grouped together. And this was thought to be true until we managed to create the hydrogen bomb and actually have nuclear fission occur. And so we did divide an atom, which gave off a whole lot of heat and radiation, and so this portion of his theory does no longer hold true. So let's look at this concept check. Which of the following statements regarding Dalton's atomic theory are believed to be true? So let's look at the ones that they give us. Elements are made up of tiny particles called atoms. That's true. All atoms of a given element are identical, and that's the one that we no longer believe is true because of isotopes existing. A given compound always has the same relative number and types of atoms. We know that's true. That's the law of constant composition. And atoms are indestructible, which is not true because that's what we just talked about with the hydrogen bomb and nuclear fission. Let's take a look at section 4.4, which is formulas of compounds. So we need to be able to talk chemistry and write chemistry, and that's what we're going to do by looking at the formulas of compounds. Remember by definition that a compound is a substance that is composed of the atoms of two or more elements and always contains exactly the same relative masses of those elements. A chemical formula then is going to express the types of atoms and the number of each type in units or molecules of a given compound, and this will be clear once we look at examples. So here's some rules. First of all, we're going to represent each atom present by looking at its element symbol, and that's what you're going to find on the periodic table. The number of each type of atom is indicated by a subscript. Now, a subscript is different than a superscript, of course. So in algebra, for example, let's say that you have x, y squared. And that means 1x and 1y. Because I could put this 1 up here, but it's not really necessary. So x, y squared. That tells me I have x times y, or 1x and 2 y's. In chemistry, we're going to write them as subscripts. So if x and y were elements, we would write them down here at the bottom like this. It's on the same side, on the right-hand side, but we write subscripts instead. And the 1, like I said before, just as in algebra, is always understood, so you don't have to put that 1 down here. When only one atom is given, you don't have to write that 1. Let's look at this example with sulfur trioxide. This is the proper name for this, is sulfur trioxide. You'll learn that in the next chapter. S is the symbol for sulfur, and it's capitalized. The symbol for oxygen is O, which is also capitalized. It has one atom of sulfur, so notice there's no subscript showing here indicating there's just a 1. And there are 3 atoms of oxygen, so there's a subscript 3 here for the oxygen, indicating there are 3 with every 1 sulfur atom. So let's look at this example. It says, the pesticide known as DDT paralyzes insects by binding to their nerve cells, leading to uncontrolled firing of the nerves. Before most uses of DDT were banned in the United States, many insects had developed a resistance to it. Write out the formula for DDT, and it tells you what it contains. Now, this information that's given right here isn't necessary to do the problem, but it's background information. And in chemistry, you need to start looking at the whole picture. So sometimes you're given background information that you don't necessarily need in order to do the problem or to get the answer. It's interesting. It's something that would be good to hold on to so you know it, but don't look at it as a hassle or as a pain to be able to, have to read through this and decide what you need. It's a part of the way that we problem solve in chemistry and in life in general. So you're just going to have to learn to filter out what you don't need and use what you do need. So this says right at the formula for DDT. It contains 14 carbon atoms. So I write C, which is the chemical symbol for carbon. There are 14 of those, so I'm going to put the 14 down here as a subscript. Then it says 9 hydrogen atoms, and I know from the periodic table that my symbol for hydrogen is a capital H, and there are 9 of those, so it goes as a subscript. Then there are 5 atoms of chlorine. Chlorine is capital C, lowercase l, and there are 5 of those. So this is how we would write the formula for DDT. The best way to do this always is, and we'll learn rules in the naming chapter next chapter, but when we look at this, if it tells you 14 carbon atoms, 9 hydrogen, 5 chlorine, put them in the order that they give them to you in. So just assume that's the order they want them in. So the carbon goes first. I know this is a rather large compound. It is an organic compound, meaning that it is made up of hydrogen and carbon, and we'll talk more about organic and inorganic. We name inorganics in the next chapter. And that's all you need to know to be able to do your problems for this section.